To start our differential equations course, we will start by defining a differential equation. A differential equation is an equation that contains a derivative. And along with this, we also need to look at applications which include differential equations in order for them to be useful. So we'll also define a mathematical model. A mathematical model is an equation that describes a physical application along with the definitions of the variables used. In this course, we will use mathematical models that use differential equations. One of the most common applications of differential equations involves Newton's second law, which says that force is equal to mass times acceleration. It is often the case that we can measure the forces acting on an object along with its mass, which leaves the acceleration a as the only unknown. And since a is a derivative, in particular, a acceleration is equal to dv dt, where v is velocity, this gives us a differential equation. For example, suppose that an object is falling. The forces that we will consider to be acting on this object are gravity and air resistance. From Newton's second law, we have on the one hand that force is equal to mass times acceleration, which is mass times dv dt, and on the other hand, we can measure these two forces acting on the object. In particular, the force due to air resistance is proportional to the velocity v. That is, the force due to air resistance can be written as some constant times v. We'll choose that constant to be negative gamma times v, where gamma is the drag coefficient. We'll choose gamma to be positive so that negative gamma is negative, so that the force of air resistance is acting in the opposite direction of the force of gravity. So the forces acting on our object are mass times gravity, the force from gravity, and negative gamma times v, the force from air resistance. So this gives us our first differential equation. Mass times dv dt equals mass times gravity minus gamma times v. Let's put some numbers to this example and study it further. Let's take the object's mass to be 10 and the drag coefficient gamma to be 2. Then our equation becomes 10 times dv dt equals 10 times 9.8 minus 2 times v, which can be reduced by dividing by 10 to dv dt equals 9.8 minus v over 5. Let's see what information we can get from this differential equation before we try to solve it. Since the derivative dv dt gives us the slope of v in the vt plane, we can use the differential equation to compute the slope of v at various points. For example, using v equals 40, we find that dv dt equals 9.8 minus 40 over 5, which is 9.8 minus 8, which is 1.8. So plotting this in the vt plane, we'll have that the slopes of v when v equals 40 are all 1.8. The plot of slopes of v in the vt plane that we're talking about is called the slope field or direction field. Let's compute some more and take a look at it. From the computation we just did, we know that the slopes of v when v equals 40 are all 1.8. So along the line v equals 40, the slopes of the solutions will all be 1.8. This alone doesn't give us too much detail and doesn't help us see the solutions very well. But as we compute and plot dv dt for more values of v, we get a fuller view of what our solution v of t looks like. Let's start to fill this direction field in so we get a better view of what v of t is. For v equals 50, we use our differential equation to compute dv dt equals 9.8 minus 50 over 5, which is 9.8 minus 10, which is negative 2. So at v equals 50, all of the solutions will have slope negative 0.2, almost flat. Computing more, we can look at v equals 60, then dv dt is 9.8 minus 60 over 5, which is 9.8 minus 12, or negative 2.2. So when v equals 60, all of our solutions will have slope negative 2.2. To get a good picture of what our solutions look like, we're going to need to compute the derivative dv dt at lots of values of v. While we wouldn't want to compute all of these by hand, we can use computers to compute 100 or more slopes to form a slope field very quickly. Let's outsource that work and look at what the direction field is when more vectors are computed for various values of v. With more of these direction vectors computed, a picture starts to emerge of what our solutions v of t look like. For now, I want to draw our attention to one such solution. Notice that at one v value, the tangent vectors are flat. What's happening at this red line where our tangent vectors are flat? Here, all of the values of dv dt are equal to 0. Above it, our slopes are pointing down, and dv dt is negative, and for values of v below it, dv dt is positive, and the slopes are pointing up. To find the v value here, we want to solve our differential equation for dv dt equals 0. In other words, 0 equals dv dt, which is given by 9.8 minus v over 5. Adding v over 5 and multiplying by 5 on both sides yields that v equals 49, which lines up with what we see in our direction field. So at v equals 49, dv dt is 0. In other words, v is constant. V is not changing. Since it's not changing, we say that it's in equilibrium, and we call this the equilibrium solution. We use this terminology because when something is in equilibrium, it is not changing. That is, the rate of change, derivative, is 0, as we've seen here. These equilibrium solutions will play a key role in understanding the behavior of all of our solutions. So throughout the course, we'll continue to study these equilibrium solutions in various differential equations.